This video will present the Wikipedia Vector Search Demo with Weaviate. Wikipedia is a great information source to test the next generation of search systems built on deep learning and implemented in Weaviate. This is a really great visualization of neural search because it's very intuitive to compare this to search systems that we're all familiar with, such as Google Search. This presentation will describe how information retrieval can enhance supervised learning tasks. Particularly, this is done with the Weaviate Question Answering Module. From the demo, you will know exactly how to do this yourself, supplementing downstream supervised learning inferences with additional context from the information retrieval vector search system. We'll further present the generalization of these ideas, such as how this kind of component between information retrieval and supervised learning plays out in AlphaFold 2, Frozen, GPT-3, and more examples generally of how information retrieval can supplement supervised learning tasks across data domains, again from proteins to images and text and all sorts of data types. As a reminder, this web demo is freely accessible across the world, so please check out the GraphQL console for yourself before or after watching this video. This demo is linked in the video description, as well as a pinned comment on the video. I really hope you enjoy this presentation of the Wikipedia Vector Search Demo with Weaviate. So I'm sure nearly everyone out there has heard of Wikipedia. This is one of the most exciting potential data sources for developing deep natural language processing systems. It's a really exciting source of text, data, this kind of raw text as people write sentences and paragraphs that describe all sorts of things across the world. So this is a really great source of data for testing information retrieval, these vector search engine systems, search in general, as well as labeling data for downstream supervised learning tasks, like particularly question answering in the SQuAD benchmark. To quickly explain the difference between Wikipedia and Wikidata, Wikipedia stores information in raw text form, the way is most natural for communicating information as we write articles, text messages, emails, this kind of format of organizing information in text. Wikidata contains graph-structured relations, so for example you have two nodes and then you have some kind of labeled edge that describes how these two nodes are linked to each other. So there's web demos for the vector search engines in Weaviate for both Wikipedia and Wikidata. I've made a previous video that explains the Wikidata demo, so please check that out if you're interested. And this video will be explaining vector search with the Wikipedia dataset. With our vector search engines, we're mostly interested in taking some kind of query or some kind of document and then encoding it into a vector embedding space and then finding nearby documents or nearby paragraphs within Wikipedia. But there are also some really interesting supervised learning datasets that have been built on Wikipedia as well. So in this video, we're not just going to show how Weaviate can be used for vector search and finding nearest neighbors. We're also going to see how Weaviate lets you use the retrieve then read pipeline. You can combine the information retrieval component of vector search with downstream supervised learning models to provide more context and enable them to perform better on these kinds of tasks. So quickly, let's look through these two very popular supervised learning datasets that are built on top of Wikipedia. So if you're interested in doing this research, this Weaviate tool can really help you make some progress on the KILT benchmark as well as SQuAD. This website walks you through the SQuAD 2.0 Stanford Question Answering Dataset. So we're going to walk through these two supervised learning tasks to help communicate the idea that you can use these vector search engines with the question answering module made available in Weaviate. Modules is how you interface these supervised learning tasks with the vector search information retrieval component to build these end-to-end models that do both information retrieval with vector search as well as some downstream supervised learning tasks that's enhanced by the information retrieval context for a given inference. So here's an example of two different data sets that are very popular for building on top of Wikipedia if you're interested in building on this web demo of the Wikipedia Weaviate vector search. So SQuAD 2.0, and again, because it's built on Wikipedia, it has a very diverse range of topics and information that these models have to cover. So for example, you have things like the atomic number of the periodic table for oxygen, and then you classify where in the paragraph the answer is. So this is an example of extractive question answering, where you classify the answer in the input, compared to, say, abstractive question answering, where the answer isn't directly contained in the input and the model has to generalize to producing some novel text generation that answers the question. Here's another famous dataset that is built on top of Wikipedia. KILT, the knowledge-intensive language task. So this isn't really one dataset, it's 11 datasets that are kind of summarized in this one KILT benchmark. So what it is you have a snapshot of 5.9 million Wikipedia pages. For the sake of this Weaviate demo, we're going to have about 11 million of these Wikipedia pages, and they've annotated 11 different supervised learning tasks on top of this information source. So you have things like fact verification, entity linking, open domain QA, and all these different tasks that are built on top of Wikipedia. So here's some examples of some of the supervised learning tasks that you can kind of plug your information retrieval vector search engine into, and then you have this end-to-end pipeline where you have the enhancement of the information retrieval system, something that we'll get into in more detail later in the presentation as we look through the co-search system from Salesforce Research. So here's some statistics about how the Wikipedia dataset is being hosted in Weaviate for this web demo of vector search engines. And the reason I wanted to start this presentation off by introducing these supervised learning tasks is to show you that if you want to do research in these kind of complex systems where you have to build up some kind of vector search index, you no longer would have to do that yourself if you just want to play with, say, the downstream supervised learning model that's enhanced by the context of the vector search engine. So all you have to do is just plug into this web demo if you want to do this kind of research. So here are some statistics about the Wikipedia dataset in Weaviate. We have about 11 million of these articles, 27 million of these paragraphs, and then we have 125 million of these graph cross-references. So similar to describing the Wikidata way of setting up this kind of information-heavy data set, the graph cross-references refer to how in Wikipedia you link between Wikipedia pages. So you have this very interesting kind of hybrid between text information and graph information. And in my view, that's going to be one of the most exciting things of multimodal learning, where multimodal learning is describing combining two different kinds of data modalities. And I think combining text information with graph structured information will be one of the most interesting ways of combining two different kinds of sources of encoding information. So this web demo is served, it has a cloud computing runtime, and you've got two different models. You've got these two different models from Hugging Face, one of which is what encodes the documents for the embeddings for the sake of doing cosine distance or L2 distance for the information retrieval side of this. And then you've got the downstream question answering modules. So the BERT large uncased whole world masking fine-tuned squad. This model is going to take the paragraphs that are returned from the information retrieval and is going to try to classify the answer within these paragraphs in the extractive question answering supervised learning task. If you want to know more details about how this web demo was set up and how Wikipedia was imported into Weaviate and the web demo was made accessible with the cloud runtime, please check out this article from Bob Van Light, the CEO and co-founder of Weaviate, that describes exactly how this was set up and all these different kinds of details. So now what we'll be looking through is the GraphQL interface to query Wikipedia using the Weaviate Vector Search Engine. So Bob has outlined 4 different queries that illustrate what we can do with the Weaviate Vector Search Engine and how we can query Wikipedia by using this combination of symbolic filtering as well as neural vector search. And we can also append onto the neural vector search our question answering modules. So the question answering models classify the answer within the paragraphs returned from the information retrieval component. This is the Weaviate console that lets us interface our GraphQL queries and get outputs from the Weaviate Vector Search Engine database. So this is how we ask our question answering module to answer a question with the Weaviate syntax with the GraphQL API. So first we have the get as we're returning things from the database. Then we're searching in the paragraph. So in Wikipedia we have the articles and the paragraphs. So we're searching within the paragraphs. We're limiting it to returning 1 from the search, and then we're using ask to index our question answering module. We ask the question, where is the States General of the Netherlands located? Properties content, so the content is where in the paragraph to look for it. So paragraphs are annotated with this kind of schema where content is where the actual text information is stored, and it might have meta information about the paragraph as well, like the cross-reference for the article it's contained in, or cross-references for things that it references in the paragraph. So there are all sorts of things of setting up this kind of graph-structured schema in addition to the just indexing the raw text information. In addition to the result of the question answering model, we also return the certainty of the classification. So in this case, we see a 68% confidence that this is the correct answer, classifying the answer to this question in this return document. So this is an example of how to use the information retrieval system to return this paragraph from Wikipedia and then ask this question and use an extractive question answering system, which is a classification model where it classifies the index in the input passage where the answer is. In addition to adding supervised learning models onto the output of the information retrieval model, we also might just want to use the information retrieval model for things like semantic search. So here's an example of how to search for Italian food in Wikipedia. You pass in the get paragraph, so you're searching through the paragraphs that, again, there are 27 million of these paragraphs in the Wikipedia that is indexed in the Weaviate demo. Use the near text for the nearest neighbors for the text embedding, and then you pass in Italian food, and you limit it to return 50 different results. Then in addition to the content, you also have the order. You have I think the order references as you've done the limiting, and it's a rank order of the similarity or something like that. You have the title of the article that the paragraph is sourced from. So this is how you do the cross-reference to get into the article. So in article is the cross-reference that links between paragraphs and then the overall article for the Wikipedia page. So we saw a similar example of using cross-references for news publications in the original web demo on Weaviate. So now there are 3 web demos for Weaviate. We have the news articles, Wikidata, and Wikipedia. So in the news articles, we were looking to search for things like information about Uber taxi rides, something like that was the example, and we were cross-referencing the publications. So for example, was this published in the New York Times, the Financial Times, one of these different news publications. So hopefully this is beginning to inspire your creativity about how you can cross-reference to link together different things and search through, say in my particular application, I'm looking at searching through code snippets. So I might want to search through the code itself and just search through the code as they index this paragraph. I might say code snippets, and then I'd want to know in Keras code example, and then return the title of the Keras code example. So hopefully this is beginning to inspire your inspiration about what you might be able to do with your own custom data sets, as well as understanding this application in Wikipedia. The last query demonstration illustrated a purely neural semantic search on the text of Italian food. Now let's look at how we can combine symbolic filtering to enable neurosymbolic search. So for example, when we ask, what was Michael Brecker's first saxophone, we may want to require the returned article from the information retrieval system to contain the string Michael Brecker. So this is an example of having a regular expression symbolic filtering match that filters out the results from the original information retrieval system and then enables the 2 functionalities to play together. So we have the neural search, which offers all this flexibility, but then we also kind of have the sanity check of making sure that at least the name is contained in the article by using the symbolic filters. So there are all sorts of examples of how we can use symbolic filters to enhance neural search. Here's the 4th query presented in Bob's article describing the Wikipedia Weaviate Vector Search Demo. What this is showing you how to do is how to use the graph cross-references to kind of go into the articles and then see all the paragraphs that are contained in that article. So as we search through the paragraphs for jazz saxophone players, we'll get a match in the paragraphs, then we traverse one up, say this is like a tree where its article is the parents of the paragraph, and then we go back into the paragraphs to list out all the paragraphs that are shared in this article. So for example, we look through jazz saxophone players. It takes us to this Wikipedia page, list of jazz saxophonists, and then we see the alphabetical ordering of the names of the saxophone players are the titles of the paragraphs. So then another example, alto saxophone, these are the other paragraphs, the names of the paragraphs that are contained in this article. So this is showing how to use these graph cross-references within the GraphQL vector search in order to traverse through the data objects. So thanks so much to Bob for writing this great article describing what's going on with the Wikipedia and Weaviate import and these demonstration queries that help us understand how we can perform neural vector search in Wikipedia using the Weaviate GraphQL API. Please check out this article if you haven't already. It'll be linked in the description of this video as well as pinned as a comment to the video. So now that we're armed with the technical know-how of how to use the GraphQL API in Weaviate to perform neural vector search in Wikipedia, let's take a high-level step back and go through these kinds of systems and think about what we can build with this kind of functionality. So here's a really exciting system titled CoSearch from Salesforce Research. So CoSearch is a search system built on the Cord-19 dataset. The Cord-19 dataset contains over 400,000 papers related to COVID-19, and the idea is to build these search systems that can help facilitate applications like fact verification, question answering, summarization, these kinds of natural language processing tasks by building on top of this information source. And these information sources are a very interesting overall thing of deep learning, this kind of idea of, say, unsupervised learning where we have a large amount of unlabeled data and there's some information in that data, but we're trying to figure out how to use it for these downstream kind of tasks where we annotate input-output pairs to make it very clear what kind of things we want it to do. So in this CoSearch system, we first build up the vector index, and this is what's been done already with Weaviate, and we already have this index that we can just access by using this web demo API. So if you want to do research on these downstream tasks, you can just query the Weaviate web demo and just this has already been built for you. But if you want to drill further into building up the index, you can see the different schemes of encoding the vectors, And there's all sorts of research in this area as well. So what we do is we pass these indexes, we search for, say, k nearest neighbors for the embedding of our query, and we pass that in as additional input to, say, our question answering module. We might also have something like a re-ranking model that processes the outputs, all sorts of things of connecting these different components together to build these really interesting natural language processing systems. So I think this is a really interesting paradigm of retrieve then read models, and particularly studying this in natural language processing. On the retrieve side, we have things like search, where we train these information retrieval models, say contrastive learners, where we're evaluating them based on the similarity comparison of two vector representations of documents that we've labeled to be similar, or maybe we've been able to use data augmentation to determine these two documents are similar, or more likely images are similar. In the search task, we also have, say, re-ranking, where we have these where we return some kind of core set of documents from the retrieval component, and then we have a supervised learning model that re-ranks the documents, and we might additionally pass the re-ranked documents as input to the supervised learning model. And then we also have question answering as this kind of theme of like a search task as you ask questions to a search engine. Then we have these downstream supervised learning tasks. I think fact verification is very interesting, question answering, and also topic classification. All these different downstream supervised learning tasks could be enhanced by having more context in the input from the retrieve models. To further motivate your interest in these retrieve then read models, I want to point you to the paper Challenges in Generalization in Open Domain Question Answering. And if you're curious, I've made a full paper summary video of this paper on Henry AI Labs. But basically the high level finding is that they study different kinds of generalization for question answering models. So for example, you can have a novel entity appears in the question, like say the green eggs and ham entity has never appeared in the training set. Compositional generalization, where you're recombining different parts of the training set to make up or compose novel test instances, and so on. So they break down these different kinds of required generalization for question answering systems. You see this example again, just if you want to pause it and look through this. These are examples of breaking down the kinds of generalization that's required for solving open domain question answering. And open domain question answering, similar to Wikipedia, that's where you have to answer a very diverse range of questions. So it could ask you a question about oxygen and then something about Florida, or this kind of super diverse set of information. So what they find in this paper is that these retrieve then read models like retrieval augmented generation, the fusion in decoder, dense passage retrieval, they perform much better on these kinds of generalization cases like compositional generalization than a solely parametric language model. So say you only have the read model, and that even goes up to 11 billion parameters and trained with this salient span masking pre-training technique, which is a pretty clever pre-training technique, also BART, and you see the compositional generalization score is just way lower. Retrieve then read performs much better on this compositional generalization than just having a language model. So to conclude on the idea of information retrieval and supervised learning, let's look at some examples outside of text, particularly how AlphaFold 2 uses it, and then let's also drill a little further into how GPT-3 with text adds this information retrieval in the form of in-context learning, and then let's look at Frozen, the system of combining images and text by having more context in the inputs, which we might imagine would be supplemented with an information retrieval system. And then let's get into general thoughts, things like the idea of having longer input transformers. So for example, the paper titled Beyond 512 Tokens, things like Big Bird, sparse transformers, this idea of trying to have inputs where you could have, say, 4,096 tokens or massive token sequences as the inputs, such that you can utilize the information retrieval system even further, because you can provide more information to the input for one of these parametric deep learning models, and then overall you can have more information for the model to contextualize the current inference. So in AlphaFold 2, and a common practice in bioinformatics, is to use mean sequence alignment. This is commonly why in bioinformatics you study things like dynamic programming and learning how to do the Hamming distances or these kinds of distances between, say, the ACGT genetic strings. So what you do is you find these similar genetic strings by doing this kind of search retrieval, and in AlphaFold 2 you have a mean sequence alignment embedding, so you return genetically similar protein sequences to inform the current inference of the structure of this model. So this is probably one of the highest level models that exist, or like one of the most interesting applications, and you see how they're using this kind of information retrieval plus the supervised learning component. So another example of why this is so useful. And then so GPT-3 the idea of it, really what it's become is you prompt it. So it's a massive pre-trained language model with 175 billion parameters. So you don't want to have to further fine tune this thing, because to load it into memory would be untenable. So what they do is they try to provide examples of the task in the input sequence. So for example, if it's translate English to French, you give it some examples of what English to French translations look like so that it can perform the new inference of translating cheese. And it's a really interesting thing, this prompting. So there's a lot to that in addition to the information retrieval plus supervised learning component. So frozen is another really interesting idea where you prepend to the inputs images and text captions, and then it's able to perform these novel inferences. So these are some examples of combining information retrieval to supplement the input for a current inference and to enhance the downstream supervised learning capability of these kinds of models. Here are some kind of general ideas around connecting information retrieval systems like vector search engines with downstream supervised learning functionality. The beginning theme of this is that we're generally seeing these transformers try to move beyond 512 tokens. This seems mostly motivated by wanting to, take in entire documents as inputs, and this kind of idea of extending, longer paragraphs, so then when you're doing question answering or whatever it is, dialogue systems, you want to have a longer input. But we could also supplement these input windows with the returned results from information retrieval systems. So if you think longer context models like Big Bird or Transformer XL, you can use these longer input sequences, which may be advantageous for things like all sorts of things, but especially this kind of idea of information retrieval plus supervised learning for question answering. As we saw with the compositional generalization evaluation, having the additional information in the context really helps a lot with this. So then I think there's a very interesting connection between, memory and reasoning, and thinking about the interplay between these two kinds of models. So you have your information retrieval system, which is like your memory, and then you reason within your memory. If you like thinking about this kind of high-level idea around artificial intelligence and intelligent systems and how we process information. So then I think it'll be really exciting to generalize this across tasks. So this is, I think, most intuitively understood with text data, because we can compare, searching through the Wikipedia thing is very natural to how, we've all gotten used to using Google search and these different search engines to understand text data and search for text information. But this will be really interesting, and I'm personally very excited about code language search, but also image language search, all sorts of really exciting things as we generalize these kinds of systems to all sorts of data modalities and fusions between modalities. Another really exciting idea that we're exploring is training models and doing the optimization where they have this information retrieval context. So here's a really interesting paper, Meta ICL Learning to Learning Context, where the optimization in the training data is supplemented with the additional context, similar to, Google's Realm model, where you have the backpropagation all the way back to the information retrieval system, but generally this idea of getting these models used to having some kind of additional context provided in the inference and optimizing the reasoning, or however you want to describe this kind of attention across the return documents from some kind of information retrieval system. So this is a really interesting paper connecting this with meta training, this idea of few shot learning, where you divide up a data set into several smaller data sets and have this meta adaptation kind of task. But a very interesting idea of combining this information retrieval supervised learning and then fine-tuning these models to learn in context, which I think is a really awesome way of describing this. Thank you so much for watching this explanation of the Wikipedia Vector Search Demo with Weaviate. This web demo is freely accessible to anyone in the world, so please check it out after watching this video. Thanks again so much for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.